What's going on, YouTube? You know who it is. Trader Don here. We back at it again with another video. Today we're gonna be talking about quantum entanglement. We're not gonna be talking about it. We're gonna be reacting to a video. So right now, I got the video up. It's basically talking about every quantum physics concept explained in 10 minutes. So we're gonna get into this video. Don't forget, check out the other socials. Also, you're watching this video because it comes straight from the Twitch. So let's get right into it.
Entanglement. When two particles are entangled, there exists a seemingly magical link between them that can be difficult for physics to understand. No matter how far apart they are still connected, such that one particle feels what happens to the other particle. In simple terms, quantum entanglement is the situation.
Now we could think about that as a actual person between person, two atoms intertangled with each other. Now, what I feel like there's some truth to this because if you think about prayer or if you think about uh emotions, there's times where you probably were able to feel that somebody else was sad. Quantum entanglement always isn't like, oh, you're connected with this person or you're one with this person. No, it's like if you're in the same room with this person and you see them, you're most likely gonna feel what they're feeling because of their body language, because of how they look, or just because of off the energy they exude. Now, my leg is itching. My leg itching mad bad. Hold up. But because of the fact that you're able to, people just look at that as like, oh, it's just, they look sad, so I think they're sad. No, because if you're really a person that knows emotion and feels, you're gonna be able to know this person's sad on a deeper level.
Wherein certain aspects of one particle in an entangled pair depend on the aspects of the other particle, regardless of how far apart they are. Another good way of looking at it is when you have a special dice and that whenever you roll it, the same number also appears on your friend's dice, if they roll theirs. A mysterious connection exists that the best minds in physics can't explain. It challenges everything.
Wouldn't that just be transference? Quantum entanglement is just two particles transferring between each other. It's like a feed of information. Because I feel like that's a lot about, because I think, in my opinion, the human brain is a receiver and a receiver and an out. It is input and output. Okay, it's input and output, and that's why I feel like there's a lot of people in the world that probably had a thought and then saw that same thought be played out in the world. That is, I don't know, that's can't be coincidence, and that's why quantum entanglement is also about consciousness connection. So between, because you can think of it like this: quantum connection is how in the early Stone Ages there was a period of time where there's many tribes right across the world or across Pangea, and at the almost at the exact same time they all discovered weaponry. They all discovered how to make stone tools or how to mm, cook or use fire. And they have no direct connection to each other. But all of a sudden, they learn how to do something all different ways, but the same concept.
Things science knows about space and time, yet it happens naturally in our world, among atoms of living creatures, or even inanimate objects. Quantum superposition. Quantum superposition involves an object.
You ever heard like the cat in a box theory? Like if you put a dead cat in a box, or if you put a live cat in a box and put poison in it, because you can't see it, it's neither alive nor dead. Now, explaining that is very hard, so I'm gonna let him do that.
Being in multiple states simultaneously until we observe the object's actual state.
Quantum superposition is also, you can tie that into identity, because somebody can live in different aspects of themselves simultaneously, like I can. But people don't understand that, so they think, oh, this nigga's crazy. Cool, I don't care. It's called connecting the dots to explain other things.
It's like how all jigsaw puzzle pieces can be in multiple states because they can fit into any part of the picture, but it's only when you observe the pieces you know where they belong. The perfect example of an experiment that uses this concept is Schrodinger's cat. This experiment involves a cat placed inside a sealed box. Its fate is dependent on a dangerous particle in a superposition. The catch here is that no one knows if the particle killed the cat or if it survived. Only when someone opens the box will the cat's fate be revealed. So before opening the box, the cat is dead and alive, putting it in a superposition state. In short, anything can be true or false until we observe the world around us.
No, Schrödinger cat. They just made a better depiction of also quantum superposition. Whatever you see in the world doesn't ultimately come to fruition unless you observe it. So you can say somebody is a, let's say, horrible person, but you have no evidence to see that they are neither bad nor good until you observe them, and then you understand what they are. That's a human way of looking at Schrodinger's cat.
Similarly, a particle in quantum superposition can exist in multiple states until it is observed. Returning to the jigsaw puzzle analogy, we only see where the pieces fit until we observe them and the bigger picture. Quantum physics tells us that everything in the world is possible until the moment of observation. Heisenberg's uncertainty principle. You're in a scenario where you're trying to catch a mosquito that has been bugging you for a while. The more you focus on its position, the less you know how fast it is. Similarly, if you focus on its speed, you won't be able to observe its exact position. Heisenberg's uncertainty principle operates in the same way. Heisenberg's uncertainty principle states that it is impossible to simultaneously and precisely know the position, speed, and direction of a quantum particle due to the limitations in measurement accuracy. This principle is like a balancing act. It's rooted.
Honestly, that is also true for people that are outside of a box. Because I want to hear it again so I can fully complete this thought.
Of a quantum particle due to the
He said something
simultaneously and precisely know the position, speed,
the position, speed,
and direction of a.
That is also true for any human that's outside of that hasn't been put inside a box. You cannot determine their speed, direction, or path because of the fact you don't know them. Or your focus is so much on them that it's only on a specific point that you can't see the bigger picture.
Quantum particle due to the limitations in measurement accuracy. This principle is like a balancing act. It's rooted in the observer effect, which states that observing an object will change its behavior. So if we measure a tortoise moving at 0.5 miles per hour, we know its momentum, but not its exact position, because it is now in a constant state of motion. But if we measure its exact location, we won't be able to get its exact speed, because we are now focused on where it is, rather than how fast it is going. The uncertainty principle is Heisenberg's way of telling us that there is no absolute certainty in pinning down particles' exact position and momentum in the quantum world, where uncertainty rules over certainty. Quantum tunneling. In the quantum world, particles can do something impossible, pass through impenetrable barriers. Classical physics says this is impossible because one particle can only occupy.
You ever seen it's like when the flash phases through objects. Quantum tunneling? If we ever are able to reach quantum tunneling, that would literally us be reading hyperspeed, wouldn't it? Like we'll be able to just jump through space.
One space at a time. How does a particle pass through a barrier if that's the case? That's the principle of quantum tunneling. Think of it as similar to how you try to walk through a closed door, but suddenly find yourself on the other side without trying to open it. But it's not like you found a secret passage. Similarly, particles cannot access a passage that can penetrate barriers. But the quantum world tells us that these particles have a unique teleportation ability to do what seems impossible. The universe says, hey, I'll give these particles the ability to sneak through walls, even though you thought they were impenetrable. But this is not because of a mystical ability. Instead, it's due to the wave-like nature of particles, which allows them to simultaneously exist on the other side of an impenetrable barrier. The catch is that quantum tunneling is less likely to happen the higher an object's mass is, making it unlikely for objects larger than a particle to pass through barriers. So you might want to forget about teleportation, because it's unlikely to happen anytime soon. Quantum computing. Regular computers are capable of two things. They can either be on or off. But let's say they're
Quantum computing is literally like your brain. It's quantum computers are able to do multiple tasks all at once, or have multiple things being taught to it, or being made using multiple, what's the word, variables.
There's a quantum computer that has superpowers in the sense that it can be on, off, or both on and off simultaneously. That's the basic principle behind quantum computing. In the regular world, computers exchange bits that can only be 0 or 1. However, in the quantum world, computers exchange quantum bits, or qubits, which can exist in multiple states simultaneously because of quantum superposition. So these bits can be 0, 1, or both 0 and 1 at the same time. In this case, superposition allows quantum computers to process information much faster than regular computers. They can do multiple tasks simultaneously while taking on multiple routes, allowing them to solve the most complex problems until they reach a solution. Of course, quantum computers use quantum mechanics to solve problems that even supercomputers aren't capable of. The double slit experiment. The double slit experiment can be explained in a situation where you have a small cannon that can shoot tiny marbles toward two slits, and there's a wall behind the slits. In classical physics, you're supposed to see two bands on the wall because the marbles are supposed to split and pass through the two slits. However, the double slit experiment has a different result. In this experiment, interference patterns that can only be exhibited by waves will appear in the wall behind the slits when particles are shot through double slits. But how is this possible? If you recreate the same experiment using the example we used about the marbles, you will get two bands on the wall. However, for particles, ripples will appear, as if the particles behave like waves instead of solid balls. The double slit experiment suggests that particles have a dual nature, in that they can be solid or act like waves. But the trick here is that the particles only exhibit this behavior when they are shot through slits. It's like a magician pulls off the old switcheroo within the slits and changes the particles into waves. This experiment shows that things in the quantum world don't always behave as classical physics tells them to. Particles can have a
Just the fact that it doesn't behave how we think. Quantum mechanics doesn't behave how we think it would. It is very randomized.
dual nature in that they can exhibit wave-like behaviors under certain circumstances. The exact reason for this behavior is the subject of ongoing studies. This is why the double slit experiment only supports the theory, but does not prove it. Wave-particle duality. In the quantum realm, particles can showcase a dual nature. A particle behaves like a particle when observed, but when unobserved, it can display properties similar to a wave, exhibiting
It's like people with fake personalities, false identities. When they observe, they look good, they look proper, they look well made. But behind closed doors, that's all I gotta say.
interference patterns. The challenging part here is that particles and waves are supposed to behave differently according to classical physics. However, in the quantum realm, particles have the dual properties of both a particle and a wave. Experiments like the double slit experiment showcase this duality, but it's not as if the baseball in your hand can suddenly turn into a wave. It's much more complex than that, and rooted in the unique and uncertain aspects of the quantum world. The uncertainty principle also plays a role here. Depending on our observation, the innate uncertainty of particles in the quantum world contributes to their dual nature, making them exhibit particle-like or wave-like properties. This ultimately means that particles, when observed in the quantum world, are versatile and can play different roles depending on the situation and how you observe them. Quantum field theory. In the quantum field theory, at every single time, there exist different types of fields that we cannot see. These fields can be magnetic fields, electric fields, or gravitational fields. All these fields have unique properties that have different effects on certain objects or particles. When these fields interact, they create scenarios where particles behave in various ways. Simply, when you toss a pebble into a
force field.
pond, it creates ripples through the water. That pebble is a particle. Every particle has a quantum field, represented by the ripples created by a pebble thrown into a pond. When these particles interact with
reach
one
below
another,
the
the
threshold.
fields interact as well. So if you throw two pebbles into a pond simultaneously and close to one another, you will see their ripples either turning into a wave or canceling each other out. But instead of a pond, the quantum field theory appears more like a dance floor. When the fields generated by the particles interact, the particles will start to act like dancers, twirling on the dance
I
floor,
understand. People
spinning,
might not-
jumping, and moving around.
I understand people not like videos like this, but it's only because I'm very intuitive and I like to learn things about this world and also connect other things to stuff that I learn to other things in this world. So that's why you would never see me list knowing one thing. I'm over here just trying to learn everything. Because I said this before, a wise man doesn't know everything, but wants to know everything, but understands he doesn't know everything, but knows a lot.
Around from one place to another. The quantum field theory tries to unify the movements created by all the particles interacting. It provides a framework often used in quantum mechanics and explains the quantum world and the different things happening in the most miniature observable world of atoms and particles. The observer effect. Say you wanted to take pictures with your camera after observing a particular scene. For example, you want to capture a scene of two lovers kissing, but when you look at the photo, the scene changes into two people fighting each other. This is similar to how the observer effect works. In the quantum world, observing particles can influence their actions. On the other hand, in the everyday world, observing things for what they are doesn't change their nature or what they're doing. But in quantum physics, particles are shy enough to change their behavior when they know you're observing them.
Yeah. I for a long time, that is true because being observed will make people uncomfortable when you see them, when you know what's going on. But does it really matter? Like, does it matter? Because being observed, being watched is like, okay, I guess.
It's like someone is invisible only whenever another person is looking at them. Observation is commonly supposed to be a neutral act.
It's also like how when you're with a person, y'all realities are connected, quantum entanglement, your realities are connected. That means y'all are both having the same experience at one time. When y'all leave, y'all no longer in the same experience. Y'all living your own experience.
That doesn't change the outcome of an experiment or any observable phenomena. A house will always be burning if you observe the flames turning wood into ash. In the quantum world, however, observing particles' actions can change how they act. And there's a reason why this makes sense.
Why, though?
Picture this. You aren't observing anything in a pitch black room that's too dark for anyone to see. But when you turn your flashlight on, the room changes from dark to semi-lit simply because you used a tool to try to observe your surroundings. You can also picture it as putting a thermometer in hot water. Because the thermometer is colder than the water in the pot, adding it to measure the water's temperature will slightly alter the water's temperature compared to what it was before. That is basically how the observer effect works. Observation can change the behavior of atoms because measuring tools can already have a huge effect on the small events happening in the quantum world, where even a speck of dust is already an entire planet larger than an atom.
Alright. So if y'all like this video, let me know. If y'all want more reaction videos, comment down below. And don't forget to like, comment, and subscribe. And we're gonna have a good day. Peace out. And don't forget to go look at the Twitch.